In our last video, we started looking at simple harmonic motion, what it is, and we started looking at a few of the simple equations of simple harmonic motion. We're going to look in this video a little more at those equations. So we found these equations last time, the period and the frequency of a simple harmonic oscillator. The period, of course, being the time it takes for one full cycle. So you have a spring at a maximum amplitude, it goes to a negative amplitude, then back to a maximum amplitude. That time would be your period. Then the frequency would be 1 divided by that period. So the period we found to be 2 pi times the square root of m over k. Frequency would just be the 1 over that, so 1 over 2 pi times the square root of k over m. Well, we're going to use this right now to form what we call the angular frequency. It's basically the angular velocity that we learned back in rotational motion. But we're calling it angular frequency now because it's not full circular motion, it's just an oscillation, so angular frequency. Anyway, here's how we get that. Remember that velocity in uniform circular motion would be the distance over time, so one full cycle would be 2 pi r, the circumference, divided by the time, which is your period. But also remember that your angular velocity, or in this case angular frequency, is just velocity divided by the radius r. That gives us that the angular frequency is 2 pi divided by the period. But 1 over the period is just the frequency, and we also have the fact that period is 2 pi times square root of m over k, and frequency is 1 over 2 pi times square root of k over m, so we can combine all that to get these three different forms of angular frequency. We get 2 pi divided by the period, or 2 pi times the frequency. Those are both come straight from this equation that we just derived. But the frequency is 1 over 2 pi times the square root of k over m, and when that's multiplied by 2 pi, it gets rid of the 1 over 2 pi, and you're left with square root of k over m. So here are three simple equations to calculate the angular frequency. Now this variable is very important for the equations of motion, as we will see in just a moment. We ended up last video talking about this equation, talking about the position of a simple harmonic oscillator. So here, the graph on the left, you're looking at position as a function of time. And you can see that the position, if it starts at a positive amplitude A, follows some cosine function. Well, we also we know that cosine has to be of some angle theta, but omega is equal to theta over time t, so this becomes A times the cosine of omega t. Now, what is the omega? Well, it's what we just found out in the last slide. Omega can be 2 pi f, or it can be 2 pi over the period t. And so you get this simple equation for finding the position of a simple harmonic oscillator at any point in time. Now, I want you to notice something here. If you wanted to, you could shift the curve by a quarter period. So, whereas you started at a maximum up here and ended at a maximum at period t, we do that actually quarter of a period later in the second graph. And the result is that you actually end up having a sine function instead of a cosine function. Well, it turns out that both will work, but you do want to use the one that you start with. So if you start with if you start a simple harmonic oscillator at 0, you'd use a sine function. But if you started at some amplitude A, you'd use a cosine function. However, very infrequently, very rarely are you going to have this situation. And so we just use the cosine function. But that's an important point to note, is how how this could be used either as a sine or cosine function. Okay, so let's go a little further. We talked about position here, and we know the equation for your position. That would be x equals a cosine omega t. But remember that the velocity is the slope of x. So if we look here, we're going to look at 5 different points. Here we have a slope of 0. Here we have a negative slope. Down here we have a slope of 0. Here we have a positive slope. And here we have a slope of 0 again. So theoretically, we should have, for your velocity, a slope of 0. And then at quarter t, you should have some negative velocity. And then at 1/2 t, you should have a 0 velocity. 3/4 t, you should have a positive. And then at t itself, back down to 0. Looks like you have a negative sine function. Now, I don't do this graph justice, so we'll let the author do that. This is what the velocity graph would look like. And sure enough, the velocity does form a negative sine function. So what's the equation for velocity? It would be velocity is the negative maximum velocity value times the sine of omega t, which omega we know is just 2 pi over t over your period t. Now there is another way to describe this. Remember that V max can be written as a omega. In a previous slide, we had an equation for V max. If you look at that equation, you'll see that that equation is just simply the amplitude times the angular frequency. And so knowing that, our final equation becomes that the velocity is equal to negative a omega times sine of omega t. All right, let's take a look at acceleration. Just like velocity is the slope of the position graph, likewise, acceleration is the slope of your velocity graph. So let's take a look at your slopes. Here at time 0, your velocity graph has a negative slope, which means for acceleration you would have some negative acceleration. At quarter t, you have 0 slope, which means your acceleration should be 0. At 1/2 t, you have a positive slope. And then at 3/4 t, you have a 0 slope again. And at t, you have a negative slope. So we end up with a negative cosine function. Again, I don't do it justice. Here's what the author does. Sure enough, it's a negative cosine function. So the equation would be acceleration is equal to negative some maximum acceleration value times the cosine of omega t, omega just being 2 pi over the period. So just like we saw last time that Vmax, in the last slide, that Vmax is equal to a omega, turns out that your maximum acceleration is going to be a omega squared. And that's an easy one to show. If you have questions on that, just email me. I'm happy to show it. I believe the author does show it as well. So your final equation becomes this, and I just noticed this should not be little a. This should be capital A, your amplitude. So it would be acceleration is equal to negative amplitude times angular frequency squared times cosine of omega t. So bottom line, you have your simple equations of motion where position is amplitude times cosine omega t. Velocity would be negative amplitude times angular frequency times sine omega t. And your acceleration would be negative amplitude times angular frequency squared times the cosine of omega t. All of this, remembering that omega, your angular frequency, is going to be 2 pi over the period. It's also equal to 2 pi times the frequency, and it's equal to the square root of the spring constant divided by whatever mass is on your oscillator.